Two of the most challenging scientific mysteries in astrophysics occur in a region that we call solar corona.
Have you ever dreamed of touching the sun? Well, you'll have to wake up because that's not going to happen, but you can live vicariously through the topic of today's video. The Parker Solar Probe has become the first spacecraft to touch the sun, 60 years after NASA set the aim and 3 years after it launched. Stay tuned until the end of the video, where we'll be discussing the Parker probes and giving you all you need to know about them, including things we've already discovered thanks to the Parker probes. The Parker Solar Probe has become a hot topic after being the first man-made object to touch the sun. With its solar probe cup, it passed directly through the sun's corona at a distance of just 13 million kilometers, sampling the first solar particles and magnetic fields. The mission, named for astronomer Eugene Parker, was launched from the Cape Canaveral Air Force Station on August 12, 2018. With the goal of unraveling the secrets of the sun's atmosphere hidden beneath its brilliance. Its goal is to provide the closest ever observations of a star and to aid in the understanding of the sun's changing circumstances and their impact on the Earth and other planets. The Parker Solar Probe will travel as close as 3.8 million miles to the sun's surface and will be subjected to severe temperatures. The Thermal Protection System, TPS, is a hexagonal carbon heat shield that protects the probe from the heat and radiation of the sun. The TPS will be exposed to temperatures of up to 2,500 degrees Fahrenheit when it is closest to the sun. The probe's equipment will also be used to answer concerns about the genesis and evolution of solar winds, allowing scientists to better predict changes in Earth's space environment and preserve lives and technology. Scientists have built a probe with a 4.5-inch thick carbon composite heat shield that can resist temperatures of up to 1,377 degrees Celsius, ensuring its survival in the harsh conditions near the sun. Because of its capacity to remove heat from its surface, carbon was employed to make the heat shield. As there is no air in space, and heat requires a medium to pass through, the only option to discharge heat energy from the shield is to produce photons and scatter light. As a result, a white coating is applied to the shield's top to help reflect heat and light. The heat shield is located at the probe's end and will always be directed toward the sun. A sensor extending slightly beyond the probe can detect whether or not the probe will be exposed to the sun. The Parker Solar Probe mission. According to NASA, the Parker Solar Probe has 3 major goals. The probe's mission, according to NASA, is to trace the flow of energy that heats and accelerates the solar corona, the sun's atmosphere, and solar wind, determine the structure and dynamics of the plasma and magnetic fields at solar wind sources, and investigate mechanisms that accelerate and transport energetic particles. Solar winds, the solar corona, and why they exist are all mysteries. The probe's data may provide insight into how these events operate. Information might potentially be utilized to prevent natural disasters in the future. When coronal mass ejections collide with the Earth, they can generate a geomagnetic storm, which can disrupt the magnetosphere. A coronal mass ejection, for example, created a catastrophic geomagnetic storm on March 9, 1989, resulting in power outages in Quebec, Canada. By examining the corona, more can be learned about why these mass ejections interact with magnetic fields and how to deal with them when they are aimed towards Earth. Another question we aim to address with the Parker Solar Probe is how certain particles may accelerate away from the sun at incredible rates, up to 90,000 miles per second, or more than half the speed of light. Because these particles travel so fast that they can reach Earth in less than half an hour, they can cause electrical interference on satellites with little warning. So, why is it that the Parker Solar Probe hasn't melted? The difference between heat and temperature is the key to understanding. Heat is the total amount of energy transferred by particles, whereas temperature is the rate at which they move. The corona is extremely thin, and there are relatively few particles to transfer energy to the spacecraft. As a result, while the particles move fast, because of the high temperature, they don't transmit much energy to the spacecraft, low heat. It's like placing your hand in a hot oven versus a pot of boiling water. Don't do this at home. Your hand doesn't become nearly as hot in the oven air as it would in the much denser water of the boiling pot. Did it actually reach the sun's surface? Well, what it means to touch the sun takes some clarification, as the sun doesn't have a solid crust like Earth. However, the space agency is claiming that the Parker probe made contact with the sun's surface since it was discovered to have sampled particles. The event happened in April, but scientists could only confirm it after examining the data. To put it another way, while the sun doesn't have a solid surface, it does have an invisible border where solar material may divorce from its source and flee outwards, a phenomenon known as the solar wind, which the mission is working to understand. This boundary is known as the Alfvén critical surface, after the Swedish Nobel laureate Hans Alfvén, who made several significant contributions to plasma physics. The latest achievement is a huge step forward for the Parker Solar Probe and a giant leap forward for solar research. Touching the sun allows scientists to learn more about our nearest star and its impact on the solar system, much as landing on the moon helped them to learn more about how it was formed. Well, you might be wondering what the probe revealed. In 2019, the Parker Solar Probe discovered that remarkable magnetic zigzag formations in the solar wind, known as switchbacks, are abundant close to the Sun. Switchbacks are found in patches and contain a larger amount of helium, which is thought to come from the photosphere than other components. This piqued people's curiosity about the characteristics and prompted more inquiries. What were their origins? Were they created on the Sun's surface, or were they fashioned by a mechanism that twisted magnetic fields in the solar atmosphere? The Parker Solar Probe has now found one location where such characteristics originate, having cut its distance to the Sun in half since then, the solar surface. On April 28, 2021, while pursuing its 9th flyby of the Sun, the Parker Probe got as close to the solar surface as 13 million kilometers, ultimately entering the solar atmosphere for the first time. For the next 4 years, the probe will make flybys of Venus in order to spiral closer to the Sun, eventually reaching a distance of 6 million kilometers from its surface. During the April flyby, Parker weaved in and out of the corona numerous times, which helped physicists realize that the barrier known as the Alpine critical surface isn't a smooth circle around the Sun. Instead, it is characterized by spikes and troughs. Understanding the presence of these structures may help scientists correlate them with solar activity observed on the Sun's surface.
A small amount of illuminated surface produces enough energy to power up the spacecraft and all of the instruments.
Parker had another interesting encounter during the flyby, passing 6.5 million miles from the Sun's surface. It traveled through a feature known as the pseudostreamer, which is a huge structure that rises above the surface of the Sun and may be seen from Earth during solar eclipses. Conditions quieted within the pseudostreamer, particles slowed, and the number of switchbacks decreased, a stark contrast to the bustling onslaught of particles the spacecraft normally faces in the solar wind. For the first time, the spacecraft encountered an area where magnetic fields were strong enough to obstruct particle transport. While the new results pinpoint the location of switchbacks, the scientists are unable to confirm how they are generated. According to one idea, they are caused by plasma waves that sweep around the region like ocean waves. Another theory claims they're formed by an explosive process known as magnetic reconnection, which occurs at the intersections of the magnetic funnels. Parker's closer visits may yield more hints about switchbacks and other solar phenomena now that experts know what to look for. Scientists will be able to see into an area that is crucial for superheating the corona and propelling the solar wind to supersonic speeds, thanks to the data that will be released soon.
During solar encounters, the Sun itself blocks Parker Solar Probe from receiving commands from the Earth.
A little fact for you, the Parker Probe has already shattered the world record for the fastest spaceship. On November 21st, the Parker Solar Probe set a new speed record for a spacecraft when it flew towards the Sun at 586,864 kilometers per hour. The spacecraft, which is currently traveling at an even faster speed, got within 8.5 million kilometers of the solar surface on its 10th solar approach. If you enjoy what you've seen thus far and want to see more, check out our video on NASA's insane discovery with James Webb Telescope. So what do you think about the Parker Probe? Are you excited about what this can help us discover in the future? Let us know your thoughts in the comment section below.